Hello friends, your physics companion IBM is here to bring you another episode of multiple choice questions in waves. This is going to be part 3 of solved past paper questions of AS multiple choice questions. Remember I said in all the parts that waves will contribute the biggest percentage to your progress or to your performance in paper 1. So waves with electricity should take much of your revision time, especially when you are preparing for multiple choice questions. Without wasting time, let's begin part 4 from where we stopped in part 3. So in part 3, I think we stopped on page 778 and I want us to progress to page 79. Okay, so the displacement distance graph for a transverse wave, for a transverse progressive wave is shown here. The phase difference between points x and y can be expressed as 180 times n degrees. What is the value of n? So let's try to establish n. Let's assume x is here, and if it is at maximum displacement, then y is here, it is also at maximum displacement. So we can find the distance out of step of these 2 points in terms of wavelength. This could be the distance out of step in terms of wavelength. So this is this will be, if I start from this point to this point, that is one wavelength, and of course this is going to be from one peak to another peak, and that is a half wavelength. So we have one wavelength plus a half wavelength, which is going to be 3/2 wavelength. So it means the phase difference phi is going to be equal to 360 degrees into the distance out of step over wavelength, which is going to be 360 into, where there is x, I'm putting 3/2 lambda, or 1.5 lambda, divided by lambda. So lambda cancels out, and this means I will get 360 times 3 divided by 2. Let me pick my calculator. Okay, from my calculator, 360 times 3 divided by 2, that gives me 540. So this is 540 degrees. So it means 540 degrees should be equal to 180 times n in degrees. So it means n is going to be 540 divided by 180, which is 54 divided by 18, which gives us 3. So n must be 3. So our answer is going to be C. So note how I cancelled out wavelength, because a phase difference is going to be simply 360 degrees into the distance out of step of the 2 points divided by wavelength. So n is going to be 3. The 4 graphs represent a progressive wave on a stretched string. Graphs A and B show how the displacement d varies with the distance x along the string at one instant. Graphs C and D show how the displacement d varies with the time t at a particular value of x. The labels on the graphs are intended to show the wavelength, the period, and the amplitude A, but only one graph is correctly labeled. Which graph is correctly labeled? So it is a graph of displacement against distance. So this cannot be period. Displacement against distance, this can be wavelength, but this is not amplitude, because amplitude is just the distance from equilibrium position in one particular direction. So this one is not also going to be correct, just like this one. Then this is distance against time, so this can't be wavelength, it should instead be period, making it also be wrong. This is displacement d against time, this can be period, that is correct, and this can be amplitude, so the answer is D. A cathode ray oscilloscope is used to determine the frequency of a sound wave. The diagram shows the waveform on the screen. The time-based setting is 5 milliseconds per division. What is the frequency? We have already seen in some of the examples that frequency is equal to 1 over period, which is going to be 1 divided by the length representing 1 cycle times the time base setting. So this is going to be 1 over the length representing 1 cycle. We look for a most appropriate point. Okay, I'll take this part from here up here. This is 1 cycle, 2 cycles and a half. So we have 2.5 cycles. 2.5 cycles. 2.5 cycles are represented by 1, 2, 3, 4, 5, 6 divisions. No. 1, 2, 3, 4, 5, 6, 7 divisions. 2.5 cycles are represented by 7 divisions. So that means, and 2.5 is 5 over 2. So it means 1 cycle is going to be represented by 7 times 2 divided by 5. I'm saying 2.5 is the same as 5 over 2 cycles. So it means 1 cycle is going to be represented by 7 times 2 divided by 5 divisions. These are divisions, which gives us 14 over 5 divisions. So that is 1 cycle. Now if I want frequency, so where there is L, I'll put there 14 over 5 divisions. The time base setting is 5 times 10 power negative 3 seconds per division. So per division cancels with the division. So we now check our calculator. 14 divided by 5, which is that, times 5 exponent negative 3, which gives us that. Then we get 1 divided by the answer, which is 700. That gives us 71. So the frequency is going to be 71 hertz. So our answer is going to be B. A police car travels at a velocity of 3 meters, 30 meters per second, directed towards the stationary observer. It is towards. The horn of the car emits sound of frequency 200 Hz. The speed of sound is 340 meters per second. What is the frequency of the sound heard by the observer? So observed frequency is equal to V, that is the speed of sound, divided by V. Because it's towards, then this should be minus the speed of the source. Then times frequency of the source. So we want the frequency of the sound heard by the observer. So this will be equal to 340 divided by 340 minus 30, then times 2000. So just press on the calculator. 340 times 2000 divided by that is 340 minus 30, which is 310, and that gives us 2193, which is approximately 2190. So this is 2190 hertz, and that makes the answer to be D. A vibrating tuning fork is held over a measuring cylinder as shown in the figure here. Water is then gradually poured into the measuring cylinder. A much louder sound is first heard when the water level is 2.9 centimeters above the base of the measuring cylinder. A second much louder sound is heard when the water level reaches a height of 67.3 centimeters above the base. The speed of sound in air is 330. What is the frequency? So first of all, we need to find the wavelength, and I said the distance between two successive resonance points is always half wavelength. Distance between two successive resonance points, that is where we get the much louder sound, is always half wavelength. And this distance is going to be 67.3 minus 2.9. So this is going to be equal to half wavelength, which means that the wavelength is going to be 67.3 minus 2.9. This is 64.4 times 2. So this is 2 times 64.4. So that 1 times 2, we get 128.8. in centimeters. So we have the wavelength, we have the speed, now we can find the frequency. So from V equals to lambda times F, it implies that the frequency is going to be 330 divided by the wavelength, which is 128.8 times 10 power negative 2. So we have 128, we have 330 divided by 128.8 exponent negative 2, which gives us 256. So this is 256 hertz. Therefore, our answer is going to be B. A water wave in a ripple tank is diffracted as it passes through a gap in a barrier. Which two factors affect the angle of diffraction of the wave? A water wave in a ripple tank is diffracted as it passes through the gap of the barrier. Remember, diffraction is affected by two factors, that is the wavelength and the size of the gap. So which two factors affect the angle of diffraction of the wave? Number one, the amplitude and frequency of the incident wave. The amplitude does not. The amplitude of the incident wave and the width of the gap, the amplitude does not. The wavelength and the amplitude of the incident wave, the amplitude does not. The wavelength of the incident wave and the width of the gap. So this is correct. So our answer is going to be D. A double slit interference pattern using red light of wavelength 7 exponent negative 7 meters has a fringe spacing of 3.5 millimeters. Which fringe spacing would be observed for the same arrangement of apparatus but using blue light of wavelength 4.5 times 10 power negative 7 meters? Okay, so we have a double slit. The double slit equation, lambda is equal to AX divided by D. That is for Young's double slit. So we have two, we are going to come up with two equations. A double slit interference pattern using red of that wavelength. So the wavelength is given 7 times 10 power negative 7, has a fringe spacing that is X. So this will be A times X, which is 3.5 in millimeters, divided by D. We are going to repeat the same with this wavelength. So a wavelength of 4.5 times 10 power negative 7 is equal to the slit separation is the same, that is A. Then we want the fringe spacing. Which fringe spacing would be observed? So we want X, so times X divided by D. So I have two equations, I just divide them, or I make A over D the subject in one of them. So if I make A over D the subject here, it means A divided by D is going to be equal to 7 times 10 power negative 7 divided by 3.5. So I'll bring this one in this equation. So it means I'll have 4.5 times 10 power negative 7 is equal to, where there is A over D, I will put 7 times 10 power negative 7 over 3.5, then times X. So I just make X the subject from my calculator, 4.5 exponent negative 7 times 3.5 divided by 7 exponent negative 7, which gives me 2.25. So X equals to 2.25 centimeters, which is approximately, 2.25 millimeters, which is approximately 2.3 millimeters. Note that I didn't change the units for X for the first part of rate, so there's no need for me to convert the units here. The graph shows the variation of a quantity P with a quantity Q for a sound wave traveling in air. What could P and Q be? Okay, so we are saying P is directly proportional to Q. So we are saying A is saying P is amplitude and Q is intensity. That's not true. We know that intensity is directly proportional to amplitude squared. So this cannot be a line like that one. Then we are saying we have frequency and wavelength. We know the equation relating frequency to wavelength is V equals lambda f, which means that f is inversely proportional to wavelength. This cannot be a straight line through the origin like this one, so this is wrong also. Then speed and frequency. Of course, we see that V is directly proportional to frequency. V is directly proportional to frequency from this equation here, but that is only if the wavelength was constant. Then D, wavelength and period. So we know that frequency, if V is equal to lambda f, and this is going to be equal to, V is going to be equal to lambda times f, where f is 1 over t, so this is lambda over t, which implies that when I take period the other side, V times t is equal to lambda. And if V is constant, then the period is directly proportional to the wavelength. So for constant speed, the period is going to be directly proportional to wavelength. That means the most appropriate answer would be D, wavelength and period. Okay. A vibration generator produces a progressive wave on a rope. The diagram shows the rope at one instant. The wave travels at a speed of 4 meters per second. What are the wavelength and frequency of the wave? So wavelength, here we see the length. We can estimate this point here. So one cycle wavelength is going to be between 0.2 and 0.3. 0.2 and 0.3. So we can eliminate what is not in that range. So A and B are going to be wrong because they are showing that the wavelength is less than 0.2, yet one cycle starts from there and stops here. So the wavelength should be greater than 0.2. Then let's check. So these are the same, so we can check using these two. So we now check the frequency. V is equal to lambda times f. If the wavelength is 0.27 and V is equal to 4.0, so this is 4.0, then times f. So f is going to be 4 divided by 0.27. So that is 14.8, which is approximately 15. So this is going to be 15 hertz. So the answer is going to be C. The diagram shows the waveform of a signal displayed on a CRO or a cathode ray oscilloscope. The time base is set to 5 milliseconds per division. The Y gain is set to 5 millivolts per division. So the Y gain gives us amplitude, the time base gives us the period, which can be used to find the frequency. So what are the amplitude and the frequency of the signal? Let's begin with the amplitude. So the amplitude is maximum displacement from equilibrium position and is represented by two divisions. Each division is representing 5 millivolts. That means the amplitude is going to be 2 times 5 millivolts, which gives us 10 millivolts. So the amplitude is 10, so we eliminate C and D. Then we go to the frequency. One of these A or B will be correct. We check the frequency. So we said frequency is equal to 1 over period, but period is going to be the length representing one cycle times the time base setting. So this is 1 over length representing one cycle. If I start from this point up to this point, so I have 1, 2, 3, 4 divisions. So this will be 4 divisions times the time base setting, which is 5, times 10 power negative 3 per division. So division cancels with the per division. So we just check our calculator. So this is going to be 1 divided by 4 times 5 exponent negative 3, which gives us 50. So our answer here, the frequency is going to be 50 hertz. So making the answer to be A. A jet aircraft travels at a speed of 0.8 V, where V is the speed of sound. The aircraft approaches a stationary observer. The frequency of sound emitted by the aircraft is 100 Hz. Which frequency does the observer hear? It approaches. So if it approaches, the observed frequency is going to be V over V minus the speed of the source, then times Fs. So this is going to be the speed. V is the speed of sound, so I will say V divided by, again V minus speed of the source is 0.8 V, 0.8 times V, then times 100. So we notice that V has cancelled. If we common factor here is V, so this is going to be 1 divided by 1 minus 0.8, then times 100. So I'll just press the calculator. 1 divided by 0.2 times 100. So this is giving us a frequency of 500. So this is going to be 500 Hertz. So the answer is going to be D. A telescope detects and analyzes some electromagnetic radiation of wavelength 2 centimeters. I think we now know that 2 centimeters approximately microwaves or tending to radio waves, but most likely it is microwaves, because 2 centimeters is the same as 2 times 10 power negative 2, which is most likely microwaves in meters. Remenera's mother is visiting Uncle Xavier's garden. These are the electromagnetic waves. We get a guidance from the visible spectrum, where next to infrared there is red, which red is 7 times 10 power negative 7 in meters. Next to ultraviolet is violet, which is 4 times 10 power negative 7 meters. So infrared is going to be approximately 10 power negative 5, negative 6, negative 4. Then microwaves will be approximately 10 power negative 3, negative 2 in meters. Therefore, this is going to be a microwave telescope. What may be used to produce stationary waves? What may be used to produce stationary waves? A blowing air over the top of an empty bottle. I think blowing air over the top of an empty bottle will cause a node at the closed end, and there will be an antinode at the open end, making loud sound near a mountain. That one may not. Passing monochromatic light through a double slit. That may not produce a stationary wave. Passing water waves through a narrow slit. That may also not produce a stationary wave. Although it produces interference patterns, it may not produce a stationary wave. Because for a stationary wave, two identical waves traveling at the same speed must be moving in opposite directions, which may not be the case with passing water waves through a narrow slit. So the answer is going to be A. Because A, if I have a closed bottle, let's say, when you blow air here, a progressive wave travels up to the closed end and undergoes reflection. When the incident and reflected waves meet, resonance occurs and a stationary wave is formed. When the light from two lamps falls on a screen, no interference pattern can be obtained. Why is this? It is from two lamps. It is impossible to have two coherent sources of light, two lamps of light, two lamps producing light that is coherent. That is impossible. However, one lamp can produce light which is coherent if one source of light, one lamp is illuminated onto a double slit, then the two slits can act as coherent sources. But two individual lamps, the lamps have produced their light, and the phase difference or the phase changes abruptly. So we are saying the lamps are not point sources. They can still be point sources. The lamps emit light of different amplitudes. They can still emit light of the same amplitude. The light from the lamp is not coherent. So this is going to be our answer. A beam of light consists of two wavelengths, 436 nanometers, 654 nanometers. A diffraction grating of 5 times 10 power 5 lines per meter produces a diffraction pattern in which the second order, so small n is second order 2, of one of these wavelengths occurs at the same angle theta as the third order of the other wavelength. Okay, what is the angle theta? So let's come up with two equations. Remember, for diffraction grating, n lambda is equal to d sine theta. So for the first beam of light, whose wavelength is 436, n was 2, so we shall say 2 times 436 nanometers. I will not convert. Is going to be equal to, they are falling through the same diffraction grating, so this will be d sine theta. Okay, and d is given as 5 times 10 power 5 lines per meter. For the second one, it is third order, so n is 3, and the wavelength is 654. They are falling on the same, so this is falling on a diffraction grating of this produces a diffraction pattern in which the second order of one of these wavelengths occurs at the same angle theta as the third order of the other wavelength. So this is also going to be d sine theta. So the question is, what is the angle theta? What's the angle theta? So since they gave us d, we can use the first one and check. Sine theta is going to be 2 times 436. Here I'm going to be forced to convert. So this will be times 10 power negative 9 in meters divided by d. But remember, d is equal to 1 over n, where n is the number of lines. So if this is 1 over n, so it means this is going to be 2 times 436 times 10 power negative 9, then times, I'm taking n up, so it will be 5 times 10 power 5. So I can check this with my calculator. 2 times 436 exponent negative 9, exponent negative 9, which gives us that answer, then times 5 exponent 5, which gives us that. Then we can get the sine inverse shift sine inverse of the answer, which is giving us 25. So this one is giving us theta as 25 degrees. Let me check it again. A beam of light consists of two wavelengths, 536 nanometers and 654 nanometers. A diffraction grating of 5 times 10 power 5 lines produces a diffraction pattern in which a second order of one of these wavelengths occurs at the same angle theta as the third order of the other wavelength. A second order of one of these wavelengths occurs at the same angle theta as the third order. So let's check the third one. So we shall have 3. I'll just say sine theta again is going to be equal to 3 times 654 divided by times 10 power negative 9, then divide by d, but remember d is 1 over n, which n is 5 times 10 power 5. So this is 3 times 654 times 10 power negative 9 times 5 times 10 power 5. I want you to see that this is not going to be possible. We are supposed to reverse, because n is directly proportional to sine theta. The one with a larger wavelength, actually, and n is inversely proportional to wavelength. The one with the larger wavelength should have a smaller value of small n. But let's accomplish this. So this is going to be 3 times 654 exponent negative 9, which gives us that, times 5 exponent 5, which gives us that. Then let's find the sine inverse of the answer, which gives us 78, 78.8. Okay, so these angles are different, so theta is equal to 78.8. So I wanted you to see that this will not work. However, you notice that n should be inversely proportional to lambda, but n is directly proportional to theta. Therefore, the one which has a larger angle, the one which has a smaller wavelength should correspond to a larger value of n. Therefore, I will have to repeat this with the alternative values. So let me change these values so that I make this very clear for everyone to understand. So you noticed when I used them in that order, theta was not the same. But let's reverse now. Where there is n will be for a wavelength of 436 times 10 power negative 7. This is a smaller wavelength, then the order should be greater, so this will be times 3. Is going to be equal to d, which d is 1 over n. N is 5 times 10 power 5 sine of theta. So let's check sine theta. So sine theta, we shall have 5 exponent 5 times 3 times 436 exponent negative 9, which gives us that value. Then we find the sine inverse of the answer. Sine inverse of the answer, which gives us 40.8. So here theta is 40.8 degrees. We can check for the second one. For the one with the larger wavelength, we'll take up the smaller order, because if theta is the same for both, then n should be inversely proportional to lambda. So the one which has order 2, then the wavelength is going to be 654 times 10 power negative 7, which is going to be 1 over, where there is d, I'm putting 1 over n, where n is the number of lines per meter, that is capital N. So this would be 1 over 5 times 10 power 5, then sine of theta. We can check this also and see if theta is not the same. So we have 2 times 654 exponent negative 7 times 5 exponent 5. That's what we have. Sorry. 2 times 654 exponent negative 9. This is negative 9. Exponent negative 9 times 5 exponent 5. Then shift sine inverse of the answer, which is 40.8. So theta is 40.8. Therefore, the angle we are looking for here is going to be C, because we saw that if we maintained the order, theta was not the same. So we now go back to principle that if sine theta is to remain the same, and it means d is a constant, sine theta is constant, so n is inversely proportional to wavelength. The one with a large value of order, it corresponds to a smaller wavelength. A progressive wave on a wire has a frequency of 10 Hz. 2 points on the wire separated by a distance of 0.25 meters have a phase difference of 22.5 degrees. What is the maximum speed of the wave? What is the maximum speed of the wave? It is a progressive wave whose frequency is 10 Hz. 2 points on the wire separated by a distance 0.25. So we know that phase difference is equal to 360 degrees into distance between 2 points divided by wavelength. So it is a progressive wave. So they have given us phase difference as 22.5, which is equal to 360, and the distance between the two is given as 0.25. So this helps us to find the wavelength. So wavelength is going to be equal to 360 times 0.25 divided by 22.5. So we can find the wavelength 360 times 0.25 divided by 22.5. So wavelength is going to be 4 meters. The wavelength is 4 meters. Now we want the maximum speed. We want the maximum speed. Since we have the frequency, speed is going to be lambda times f. Speed is going to be lambda times f. The wavelength is 4 meters and f is 10 hertz. So the speed is going to be 40 meters per second. So the answer is going to be D. The sound from a loudspeaker placed above the tube causes resonance of the air in the tube. A stationary wave is formed with 2 notes and 2 antinodes as shown here. So before we go to any question, we can see this is a half a cycle plus a quarter. So the length of 60 centimeters is equal to a half a cycle, a half plus a quarter of a wavelength. So that means 60 is equal to a quarter, a half plus a quarter that is 4. I think that is 3/4 of wavelength. So the question says the speed of sound is 340. What is the frequency? So the wavelength here is going to be 4 times 60 divided by 3 in centimeters, which is, I think that is 20, which is 80 centimeters. So the frequency is going to be V over lambda, which is going to be 340 divided by 80 times 10 power negative 2 to change it to meters. So 340 divided by 80 exponent negative 2, which is 425 hertz, which is approximately 430. So the answer is going to be A. A police car has 2-tone sirens emitting sound of frequency of 700 hertz and 1000 hertz. The police car is traveling at a speed of 4 meters per second towards a stationary observer. The speed of sound in the air is 340 meters per second. Note that it is moving towards. What is the difference between the two frequencies of the sound that is heard by the observer? So a police car has 2-tone siren emitting sound of frequencies 700 hertz and 1000. So let's first find the first one. Remember, it is moving towards. So it means the observed frequency is going to be V over V minus Vs times the frequency of the source. So for the first frequency, the observed frequency is going to be equal to V, which is 340, times frequency of 700 divided by 340 minus 40. So this is going to be 340 times 700 divided by 310. So that is 767.7 recurring. 767.7 hertz. Let's check for the second frequency. F naught is going to be 340 times 1000 divided by 340 minus 40. 340 times 1000 divided by 310. No, that is 300. Why am I pressing 310? Divide by 300. So that is 1133 hertz. Let me check the first one again. 340 times 700 divided by 300, which is 793. 793.3 recurring. Let's subtract. So we have 1133 minus 793.3. That is 339, which is approximately 340. So the difference is 339, which is approximately 340. So the answer is going to be D. A surveyor's device emits a pulse of light. The light is reflected from a wall 150 meters away. What is the time taken for the pulse to travel from the device to the wall and then back to the device? So let this be the wall, let this be the device. The light travels from the device to the wall and back. So the speed of light is constant. The distance traveled is 150 times 2. So time is going to be 150 times 2 divided by the speed. Because it's light, this is going to be 3 times 10 power 8. Because, let me see, distance is speed times time. So time is distance over speed. So this is going to be 150 times 2 divided by 3 exponent 8. So that is 1 times 10 power negative 6 seconds, which is 1.0 microseconds. So the answer is D. This is 1.0 times 10 power negative 6 in seconds, which is 1.0 microseconds. Progressive sound waves of wavelength 20 centimeters enter the air column in a closed pipe P and an open pipe Q. The lengths of the pipes are shown. In which pipe or pipes are stationary waves formed? Of course, for an open pipe, the wavelength here is 20 centimeters. For an open pipe, if a progressive wave travels, it forms a node there, and then it undergoes reflection. So there's a stationary wave here. Even for for an open pipe, a progressive wave travels, and on the other end, it interferes with the free air and undergoes reflection. It means there is also a stationary wave formed here. So both P and Q, whether the pipe is closed or it is open, have stationary waves. Only remember that for an open pipe, all harmonics will be present. For a closed pipe, only odd. Here we only add odd harmonics. That's from 1, 3, 5, and so on and so forth. What happens when waves pass through a gap equal to their wavelength? They undergo maximum diffraction. So here they say there is diffraction and the wavelength decreases. The wavelength does not decrease. There is diffraction and the wavelength stays the same. The wavelength does not change. Two sources of microwaves, P and Q, produce coherent waves with a phase difference of 180 degrees. The waves have the same wavelength, lambda. At the point S, there is a minimum in the interference pattern produced by the waves from the two sources. Distance QS minus PS is called the path difference. In the expression shown, n is an integer. Which expression represents the path difference? So number one, we said in one of the examples, if P and Q had a phase difference 0 out of phase, and the maximum is formed here, then the path difference would be n times lambda. If this had phase difference 0 and the maximum is formed here, this would be n lambda. If it was a minimum, then it would be n plus a half of lambda. In other words, it is an odd number multiplied by half wavelength. But now the phase difference here is 180 between the two sources. That means if there is a minimum here, then the path difference must be that for a maximum, because the phase difference between the sources was actually 180 degrees instead of 0. I repeat myself. If the phase difference between the two sources P and Q was 0, for a minimum to be formed at S, the path difference would be this. But if a minimum is still formed at S, yet the phase difference is 180 degrees, then it means the path difference is like that of a maxima when the phase difference was 0. When the phase between P and Q is 0, and here we have a maximum, when the phase difference is changed to 180 degrees, the interference pattern is swap positions. Where we found a maximum, there will be therefore a minimum. Therefore, I am saying, since it is a minimum at S, if P and Q were having a phase difference of 0, we would say the path difference is this. But since P and Q have a phase difference of 180, then the path difference is going to be that of constructive interference. So this means the answer is going to be A. A parallel beam of monochromatic light of wavelength lambda is incident normally on a diffraction grating G. The angle between the directions of the two second order diffraction beams at P1 and P2 is alpha. So this angle here is going to be alpha over 2. It is the most important angle. What is the spacing of the lines on the grating? So for a diffraction grating, we know that n lambda is equal to d sine theta. So it is second order, so twice our wavelength is going to be d. What is the spacing of the lines? The spacing is d, so it is going to be d sine of alpha divided by 2. So making d the subject, d is going to be twice alpha divided by sine of alpha divided by 2. So it means our answer is going to be exactly C. A progressive sound wave in air has amplitude x0, intensity I. The amplitude of the wave increases to 3x0. What is the new intensity of the wave? So we know that intensity is directly proportional to amplitude squared. So for the first wave, intensity is equal to x0 squared times the constant k. For the second wave, the amplitude of the wave increases to 3x0. The second intensity I2 is going to be k. Where there is amplitude, I will put there 3x0, but this is squared. So the second intensity is equal to a constant k times 9x0 squared. But remember, k times x0 squared is I. So it means the second intensity I2 is going to be equal to 9 times I. So our answer here is going to be D. This is k times x0 squared is the same as I. That's why I said kx0 squared becomes I, then we remain with the 9. So that is 9I. The variation with the distance x of the displacement y of a transverse wave on a rope is shown at time t equals to 0 here. The wave has frequency 0.5 Hz. At point t, at point x on the rope is marked. The point x on the rope is marked. The diagram shows the original position of x and 4 new positions of x at time t equals to 1 second. Let's first see what is 1 second. Let's first find the period. Period is equal to 1 over f, which is 1 over 0.5, and I think this is going to be 2. 1 divided by 0.5, I think that is 2. So the period is 2 seconds. 1 second is equal to half of a period. So we are starting with point x at maximum displacement upwards. So a quarter a cycle will go to position M, then half a cycle will go to position B, and then it continues upwards, and so on and so forth. That means at t equals to 1 second, which is half a cycle, it will be at position B. A sound wave is detected by a microphone. The output from the microphone is connected to the Y input of a CRO. The trace on the CRO is shown in the figure. The time base is set to 0.2 milliseconds per division. What is the frequency? So we know that to find the frequency, we need it is 1 over the period, which is 1 over the length representing 1 cycle, times the time base setting, times the time base setting. I'm going to call it X, time base setting. Okay, let's see the length representing one cycle. I'll draw a horizontal line through this so that I can see one cycle. If I start from here, one cycle stops here. 1, 2, 3, 4. There are 4 divisions, so the frequency is going to be 1 over 4 divisions times the time base setting, which is 0.2. We multiply by 10 power negative 3 to remove milli. Per division cancels with the number of divisions. So this is going to be 1 divided by 4 times 0.2 exponent negative 3. So that gives us 1250. That gives us 1250 hertz, which is automatically going to be B. A bat flies directed towards a fixed ultrasound detector at a speed of 25 meters per second, emitting pulses of ultrasound of frequency 40.0 kHz. The speed of sound in air is 330 meters per second. Which frequency does the ultrasound detector record? Of course, ultrasound is frequency above 20,000 hertz or 20,000 or 20 kilohertz. So frequency is going to be equal to V over wavelength. A bird flies directed towards an observer. So this is Doppler effect. So the observed frequency is going to be equal to V over V minus Vs times the frequency of the source. So V is 330 over 330 minus, it is traveling towards the detector with 25 meters per second, that is minus 25, then times the frequency of the source, which is 40.0, it is kilohertz. So our answer is still in kilohertz. So I will simply say 330 times 40 divided by 330 minus 25, which gives us 43.3 kilohertz. So our answer here is going to be D. It will not be C. An electromagnetic wave has wavelength 1.0 times 10 power negative 7. To which region of the electromagnetic spectrum does the wave belong? So Rumenera's mother is visiting Uncle Xavier's garden. So this is 7 times 10 power negative 7 for red in meters. The other side we have 4 times 10 power negative 7, and this is in meters for violet. So 1.0 is after 4 times 10 power negative 7 because wavelength decreases this side. This is decreasing wavelength. Towards gamma rays, wavelength is decreasing. So 1.0 times 10 power 7 is just on the right hand side of violet. So this should be ultra. This is going to be ultraviolet. So the answer is going to be B. The diagram shows a stationary wave on a string. The stationary wave has 3 nodes, N1, N2, and N3. Which statement is correct? It is actually a stationary wave. All points on the string vibrate in phase. That's not true. It is only points between 2 adjacent nodes that vibrate in phase. Points here are 180 degrees out of phase with the points in this segment here. So A is wrong. All points on the string vibrate with the same amplitude. That's also not correct. Amplitude varies from 0 at the node to maximum at the antnode. So the amplitude is not the same. Points equidistant from any two vibrate with the same frequency and in phase. Points equidistant from any two should vibrate with the same frequency and in phase. Already they are not in phase. Points equidistant from any two vibrate with the same frequency and the same amplitude. That is very true. If we consider a point somewhere here, it will have the same amplitude, and a point equidistant, the other side will have the same amplitude. So they will have the same amplitude and they will vibrate with the same frequency, but they are 180 degrees out of phase. Therefore, the answer is going to be D. In which situation does diffraction occur? Bouncing back, that is reflection, passes from one medium to another, that is refraction. A wave passes through an aperture, that is diffraction. A student connects two loudspeakers to a signal generator as shown here. As the student walks from P to Q, he notices that the loudness of the sound rises and falls repeatedly. What causes the loudness of the sound to vary? That must be interference. Regions of maximum sound and near silence are as a result of interference or are interference patterns. So this must be interference of the sound waves. Diffraction will not cause that. Doppler shift of sound, that one just raises the frequency or lowers the frequency depending on the position of the source to the observer. A parallel beam of white light is incident normal on a diffraction grating. The second order and third order spectra partially overlap. The second order, that is n equals to 2, small n is equal to 2. Third order, small n is equal to 3, partially overlap. That means theta is going to be the same if they overlap. Which wavelength in the third order spectrum appears at the same angle as the wavelength of 600 nanometers in the second order spectrum? Okay. Note that for diffraction grating, n lambda is equal to d sine theta. So they're saying which wavelength in the third order spectrum. So n is 3, the wavelength is not known. This should be equal to d sine theta. Appears at the same angle as the wavelength of 600 nanometers in the second order. So n is equal to 2, wavelength is 600. This should also be equal to d sine theta because they overlap. So we equate the two equations. You notice that 3 lambda is going to be 2 times 600, which means lambda, remember this is still in nanometers. Lambda is going to be 2 times 600 divided by 3, which gives us 1200 divided by 3, which I think is 400. So the answer here is going to be 400 nanometers. A student is investigating an electrical signal using a cathode ray oscilloscope. The frequency of the signal is 50 kilohertz. What time-based setting on the oscilloscope should be used? Okay. So frequency is equal to 1 over period. This is going to be equal to 1 over. A student is investigating an electrical signal using a cathode ray oscilloscope. The frequency of the signal is 50 kilohertz. What time-based setting on the oscilloscope should be used? So the frequency is 1 over period, which is going to be, which means that the period is going to be 1 over f, which is going to be 1 over 50,000. 1 over 50,000. And this is going to give us 1 divided by 50,000. That is 2 times 10 power negative 5 seconds. That is going to be our period. And the question is what time-based setting? What time-based setting? What time-based setting on the oscilloscope should be used? So let's check the separation of these. Let's check the length represented on the cycle by testing all these values of time-based setting. We are going to check the wavelength. So remember the period is equal to the length representing one cycle times the time-based setting. Suppose we want to check L. If L equals to period, which is 2 times 10 power negative 5 seconds, and the time base setting is 50 times 10 power negative 3 in negative 3 in seconds. So this is in seconds, and the time base setting is that. Of course, negative 50 milliseconds per centimeter. What will be L in centimeters? So that will be 2 exponent negative 5 divided by 50 exponent negative 3. So this will be very, very small. This one cannot work because it gives a very small value of L. 4 times 10 power negative 4 centimeters. This is not a very good time-based setting. Let's check the second one, which I'll check this one. I'll just put in the calculator. 2 exponent negative 5 divided by, assuming the time-based setting is 1 millisecond. So that is 1 exponent negative 3. L is going to be 0.02 centimeters. That is still very small. So this gives us 0.02 centimeters as the length of one cycle. This one gave us 4 times 10 power negative 4 centimeters. Let's check this one here. So this is going to be 2 exponent negative 5 for the period divided by, assuming the time-based setting is 10 exponent negative 6, that is 10 microseconds. L is going to be 2 centimeters. So here this gives us L as 2 centimeters, at least that one. We can even check this one. The period is 2 exponent negative 5 divided by 0.5 micron, that is exponent negative 6. This gives us again 40 centimeters, that is approximately 0.40 centimeters, that is approximately 0.4 meters. That will be very big. Therefore, the most appropriate value is going to be the best time-based setting will be 10 microseconds per centimeter, because it will give us a length on the screen of 2 centimeters for one complete cycle. What is the relationship between amplitude and intensity? We know that intensity is directly proportional to amplitude squared. Intensity is directly proportional to amplitude squared, meaning amplitude is directly proportional to the square root of intensity. Amplitude is directly proportional to the square root of intensity, which makes the answer to be C. Which statement about light waves and sound waves is correct? Both light waves and sound waves show Doppler effect. I think that is very true. Although for light it is called a redshift, for waves it is normally called, for sound it is normally called Doppler shift. So this is correct. Light waves can be diffracted, but sound cannot. All of them get diffracted. Sound waves are transverse. That is not true. Sound is longitudinal. Light is transverse. Sound waves can travel in a vacuum. That is not true. It is only light which can travel through a vacuum. The diagram shows two waves, R and S. Wave R has an amplitude of 8 centimeters and a period of 30 meters per second. What are the amplitude and period of wave S? So you see that in one complete cycle of wave R, we have 1, 2, 3 cycles of wave S. Wave R has an amplitude of 8 centimeters. So if this is 8 centimeters, then this is approximately half of 8. So it should be 4 centimeters. So we eliminate A and B. So we have C and D. Then let's check the frequency. The period of wave R is 30 milliseconds. And we are seeing that the period of S is smaller, is 1/3 of the period of R, because we see that in one wavelength, in one cycle of R, there are 1, 2, 3 cycles of S. It means the period of S is a third of the period of R. So that means this is going to be 1/3 times 30, which gives us 10. So the period is 10 milliseconds. So the answer is going to be C. A source of sound waves is traveling as shown. In which situation would the stationary observer detect the largest decrease? Largest decrease in the observed frequency. So this is observer, that is towards, that is going to be increase. Observer, still it is towards, that is an increase. Observer, it is a decrease. It is a decrease. So we have to choose between C and D. We have to choose between C and D. We can ignore these ones already. So we choose between C and D. Now it is moving. Here it is moving at 5 meters per second. It is already decreased, but it's moving at 5 meters per second. This is also a decrease, but it's moving faster. So this is going to give a greater decrease in frequency. So the answer is going to be D. M and N are two electromagnetic waves. The ratio wavelength of M over wavelength of N equals 10 power 5. What could M and N be? We are seeing wavelength of M is 10 power 5 times wavelength of N. Let's check. M is microwaves and N is visible light. Rumenera's mother is visiting Uncle Xavier's garden. So visible is here. It's about 10 power negative 7 meters. Micro is about 10 power negative 2, negative 3, negative 3, negative 4. So let's check again. You notice that if I multiply this 10 power negative 7 times 10 power 5, I get 10 power negative 2 because we add the powers. So it means M can be microwaves and N can be visible light. So this is going to be true. Note how I arrived at the answer. I know visible is of the order 10 power negative 7 meters. But of course, when I move to the left-hand side, wavelength is increasing. Microwaves is approximately 10 power negative 2, 10 power negative 3. And you notice that when I multiply 10 power negative 7 times 10 power negative 5 times 10 power 5 here, I get 10 power negative 2, which is microwave. So the answer is A. A progressive wave is incident normally on a flat reflector. The reflected wave overlaps with the incident wave and a stationary wave is formed. At an antinode, what could be the ratio displacement of the incident wave over displacement of the reflected wave at any instant? A progressive wave is incident normally on a flat reflector. The reflected wave overlaps with the incident wave and a stationary wave is formed. At an antinode, what could be the ratio? Displacement of the incident wave over displacement of the reflected wave at an antinode. Of course, at an antinode, the displacement of the incident wave is equal to the displacement of the reflected wave. So that means the ratio at that point is going to be 1. At an antinode, the displacement of the incident wave is equal to the displacement of the reflected wave. That means at that point, because an antinode, that is a point where particles vibrate with the maximum amplitude. So the displacement of the incident wave is equal to the displacement of the reflected wave. So the ratio becomes 1. A monochromatic plane wave of speed c and wavelength lambda is diffracted at a small aperture. The diagram illustrates successive wavefronts. Okay, so you see the wavelength is bigger than the size of the gap. The wavelength is slightly bigger than the size of the gap, but is almost the same after passing through the gap. After what time will some portion After what time will some portion of the wavefront GH reach point P? So we can estimate this to be one wavelength. We can estimate this distance to be another wavelength, and this is another wavelength. So distance, time is going to be distance over speed. Time is going to be distance over speed, and distance is going to be 3 wavelengths over the speed, which is c. So the answer here is going to be 3 lambda over c. So this is 3 lambda over c. I said this is the first distance covered, which is 1 wavelength. This is the second wavelength, and this is the third wavelength, and we'll have reached p. So the total distance covered is 3 wavelengths over the speed. That gives us the time. In an experiment to demonstrate two-source interference of light, a beam of light is split into two beams using two slits 0.5 millimeters apart. So this is going to be A. These two beams are incident on a laboratory wall at a distance 4 meters. So this is capital D. The wavelength of the light is 550 nanometers. How far apart are two adjacent interference fringes? So lambda is equal to AX divided by D for diffraction for the double slit. So X is going to be the wavelength 550 times D, which is 4. By the way, this is times 10 power negative 9. Then times 4 divided by A, which is 0.5 times 10 power negative 3. 550 times 550 exponent negative 9 times 4 divided by 0.5 exponent negative 3. So that gives us x. X is going to be that, which is 4.4 times 10 power negative 3. 4.4 times 10 power negative 3 in meters. And the answers here are given in millimeters. So this gives us 4.4 millimeters. So the answer would be D. A longitudinal wave travels through a long spring. The spring is shown at one instant. What is the wavelength of the spring? So wavelength is going, this part where the coils are closed, those are rarefactions. Yes, these are compressions, not rarefactions. And parts where the coils are further apart are going to correspond to rarefactions. The distance between two successive rarefactions or two successive compressions is the wavelength. Therefore, our answer is going to be B. The first compression and the next compression, the distance between them is B. A sound wave has a frequency of 2500 Hz and speed of 1500 meters per second. What is the shortest distance from a point of maximum pressure in the wave to a point of minimum pressure? Shortest distance from a point of maximum pressure to a point of minimum pressure. Okay, so let's calculate this distance. Let's calculate this distance. They gave us the wavelength and the speed. Let's find the frequency and the speed. Let's find the wavelength. So wavelength is going to be V divided by F, which is 1500 divided by F, which is 2500. So 1500 divided by 2500, that is 0.6. So this wavelength is equal to 0.6 meters. Now it is a sound wave. It is a sound wave. So let's think of a sound wave traveling. If this is the wavelength, of 0.6 meters, what is the shortest distance from the point of maximum pressure? Maximum pressure is going to be somewhere here, and in the wave to a point of minimum pressure. a point of maximum pressure to a point of minimum pressure. Okay, so let's say maximum pressure is the distance between the maximum pressure, let it be a node, and the minimum pressure is going to be the antinode if it was to be a stationary wave. Remember, distance between a node and the next node is half wavelength. Distance between a node and the next node is half wavelength. Then how about, I hope I calculated the wavelength correctly, 1500 divided by 2500, which is 0.6 meters. Okay, so the distance between two successive nodes, maximum pressure in the wave to a point of minimum pressure. So if maximum pressure is a node and minimum pressure is an antinode, and I think this will be okay, this will be a half. No, this will be a quarter wavelength. Isn't that quarter wavelength? What is the shortest distance from a point of maximum pressure a point of maximum pressure in the wave to a point of minimum pressure? The distance between two successive nodes is half wavelength. Okay, let's see if this was maximum pressure and minimum pressure. Okay, that is half wavelength. Without even wasting time, that is half wavelength, not a quarter wavelength. I will not use a stationary wave. Let me use just the above diagram. Assuming this was a wave, and here this is maximum pressure. Distance between 2 points of maximum pressure is a wavelength. That means maximum pressure and minimum pressure should be half wavelength. So this is going to be a half times 0.6 meters. So the answer is going to be B. A sound wave is displayed on the screen of a CRO as shown in the figure here. The time base of the CRO is set to 2.5 milliseconds per centimeter. What is the frequency? We have answered such questions many times. So one cycle will take 1, 2, 3, 4 divisions of 4 centimeters. And we have already said frequency is equal to 1 over period. And the period is the length representing one cycle times the time base setting. So this is 1 divided by the length representing one cycle is 4 centimeters times the time base setting, which is 2.5 times 10 power negative 3. So we have 1 divided by 4 times 2.5 exponent negative 3. So that is 100. Therefore, our answer is going to be 100 hertz. So making our answer to be B. A car traveling in a straight line at a speed of 30 meters per second passes near a stationary observer while sounding its horn. The true frequency of sound from the horn is 400 hertz. It is not that it is passing near a stationary observer. The speed of sound is 336. What is the change in the frequency of the sound heard by the observer as the car passes? We want change in the frequency. Change in frequency of the sound heard by the observer as the car passes. So if it moves towards, we have that the observed frequency is going to be equal to V over V minus V of the source times 400. So this is going to be 336 times 400 divided by 336 minus 30. So this gives us an observed frequency if it is moving towards. It is going to be 336 times 400 divided by 336 minus 30. So this will give us, this is the frequency, the change in frequency as it gets closer, but I think we are interested in when it passes near an observer. What is the change in frequency of the sound heard by the observer as the car passes? So this one is giving us 439 Hertz. Let's see when it has just passed, it has continued. The observed frequency will now be 336 times 400 divided by 336. Because it is now going, this is going to be plus 30 if it has just passed. So this will be 336 times 400 divided by 336 plus 30. So this is giving us 367 Hertz. It is giving us 367 Hertz. So let's now get the difference. So this is 439 minus 367, which gives us 72. So the change in frequency here is going to be 439 minus 367, which is 72 Hertz. So our answer is going to be C. Which list shows electromagnetic waves in the order of increasing frequency? In increasing frequency, we have Rumenera's mother is visiting Uncle Xavier's garden, with G, gamma rays having the highest frequency. So gamma rays should come at the end if it is increasing frequency. So this one is wrong, this one is wrong. And then radio waves should have the smallest frequency. So we have an answer is going to be, here we have radio waves followed by infrared, ultraviolet, then gamma. So our answer is going to be B. Radio waves, infrared, followed by gamma. The diagram shows a steel wire clamped at one end. The other end is attached to a weight hanging over a pulley. A vibrator is attached to the wire near the clamped end. A stationary wave with one loop is produced. The frequency of the vibrator is F. Which frequency should be used to produce a stationary wave with the two loops? Of course, if it is a string, Fn is equal to N times F naught. If we have one loop, that is N is equal to 1, so F1 is equal to F. So if it is two loops, it means N is going to be 2, so it means F2 is going to be twice F. So our answer here is going to be just 2F. Remember, for a string, all harmonics are present. So I can simply say Fn is equal to N, F naught, where N is equal to 1, 2, 3, 4, and so on and so forth. So our answer is going to be twice F. A parallel beam of light of wavelength 600 is incident normal on a diffraction grating. The grating has 300 lines per millimeter. This becomes 300 times 1000 to make it lines per meter. What is the total number of intensity maxima from the grating? So we know that n lambda is equal to d sine theta for a grating. N is going to be d. For maximum value of n, sine theta should be equal to 1. That is, theta is equal to 90. So n is going to be d. Remember, d is 1 over n, where n is the number of lines. So this is going to be 1 over 300,000 lines per meter. Then divide by lambda. So this is times the wavelength, which is 600 times 10 power negative 9. So we have 1 divided by 300,000 times 600 exponent negative 9, which gives us 5.5. So this gives us 5.5 or 5.6, 5.5 recurring, but n must be a whole number. And I have been emphasizing that we round off to a smaller value or to a smaller number. We don't round off to the next whole number. Therefore, this will be 5. But 5 is not the total number of maximum. If this is a diffraction grating and this is a screen, we have the central zero order maxima, that is 1. Then we shall have n above equaling to 5 and n above n below, which is equal to 5. So we have 5 plus 1 plus 5, which is 13. Which is 11. So our answer here is going to be 11. The total is 11 maxima. A pattern of interference fringes is produced using a red laser, a double slit and a screen. The screen is 3.5 meters from the double slit. The light from the laser has a wavelength of 640 nanometers. The pattern of fringes is shown in the figure here. So this is our pattern. What is the separation of the slits? So we have a bright fringe. The distance between this is going to be x, 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 and x. That means 4x is going to be 72 millimeters, which means x is equal to 72 divided by 4, 18. So x is 18 millimeters. That is the fringe separation. So what is the separation of the slits? So it is a double slit. For a double slit, lambda is equal to ax divided by d. And we want the separation of the slits, which is a. So a is going to be the wavelength, which is 640 times 10 power negative 9 times d, which is 3.5, divided by the slit fringe separation, which is 18 times 10 power negative 3. So 640 exponent negative 9 times 3.5 divided by 18 exponent negative 3, which gives us that it is 1.2 times 10 power 1, 2, 3, 4, negative 4. 1.2 times 10 power negative 4 in meters. Therefore, it means our answer is going to be A. The period of an electromagnetic wave is 1 nanosecond. 1 nanosecond. What are the frequency and wavelength of the waves? So let's start with the frequency. Frequency is equal to 1 over period. 1 over 1 times 10 power negative 9. So 1 divided by 1 exponent negative 9. So this is 3, 6, 9. 1 times 10 power 9. So I have it, this is not true, this is not true, this is not true. So the answer is going to be C. 1 times 10 power 9 hertz, that is our frequency. Which statement about progressive longitudinal waves is not correct? Progressive longitudinal waves is not correct. The oscillations of particles are parallel. That is true, they are parallel. So that is correct. They have a series of nodes and antinodes. It is a progressive. Energy is transferred. There are no nodes and antinodes. So the answer is B. It is not correct. A bicycle gear wheel is a disc with 50 teeth, equally spaced around the edge. As shown here, the gear wheel is rotated 10 times each second. In 1 second, the gear wheel rotates 10 times. Remember, there are 50 teeth, but the gear wheel rotates 10 times. That means the 50 teeth, each teeth is encountered 10 times in 1 second, which means the frequency is going to be therefore 10 times 50, which gives us 500 hertz. That is the frequency. Okay? The speed of sound in air is 330. What is the wavelength of the emitted sound? So we know that V is equal to lambda times F. So wavelength is going to be V over F, which is going to be 330 divided by 500. 330 divided by 500, which gives us 0.66 meters. 0.66 meters. So that means the wavelength is going to be A, 0.66 meters. They said a springy strip of metal is vibrated by the rotating teeth. The metal strip produces a sound of frequency that is equal to the frequency of vibration of the strip. If there are 50 teeth and the wheel rotates 10 times each second, it means each teeth, the strip vibrates 50 times 10 times, because each teeth is going to cause a vibration. In 1 second, the strip will move 10 times each second, moving around it 50 teeth going up and down. That means the frequency is F, which is 10 times 50. An ambulance travels along a straight road at a speed of 30 meters per second. Its siren emits sound of frequency 2000 Hz. The speed of sound in the air is 340. The ambulance passes a man standing at the side of the road. What is the frequency of the sound heard by the man as the ambulance moves towards him? So towards him, the frequency must be higher, so we ignore these A and B. As the ambulance moves away. When the ambulance moves away, the frequency must be lower than 2000. So we still remain with these two to check. So let's check moving. We're only going to check moving away. Moving away, because moving towards, we have already seen that these two cannot be correct. We shall just check moving away. So moving away, observe the frequency is going to be V over V. Because it's moving away, the denominator will be plus the speed of the source times the frequency of the source. So that is 340 divided by 340 plus 30, then times the frequency of the source, which is 2000. So we shall just press our calculator. 340 times 2000 divided by 370. That gives us 1837, which is 1840. So the answer is going to be D. Three different electromagnetic waves, P, Q, and R, have frequencies shown here. Which row identifies P, Q, and R? It is hard to identify electromagnetic waves by looking at frequencies, but we can easily identify them by looking at wavelength. So let's check wavelength corresponding to that. Remember, wavelength is equal to V, or speed c, over frequency. So 3 times 10 power 10, we shall have 3 exponent 8. That is the speed of light, divided by 3 exponent 10. So that is this is 0.01. That's most likely microwaves. Let's check this one. So P is most likely microwaves, because this is 1 times 10 power negative 2. So P is most likely microwaves, and that is enough for me. It means because P can't be infrared, P can't be ultraviolet, P can't be visible. I've already verified it is 0.01 or 1 times 10 power negative 2 meters, and this is microwaves. From Rumenera's mother is visiting Uncle Xavier's garden. Here this is 10 power negative 7 visible, 10 power negative 5, negative 6, negative 4. This is 10 power negative 2, negative 3. So that means the answer is going to be microwaves, infrared and visible. Which law describes the oscillations of two moving particles in a stationary wave that are separated by a distance of half a wavelength? In a stationary wave, separated by a distance, that are separated by a distance of half a wavelength. Let's think of a simple demonstration of a stationary wave. Two particles, they are moving particles, so it means we can't think about the nodes. So we must think about here. So if they are separated by half wavelength, by all means one particle must be in one segment, another one will be in another segment. That means the phase difference is 180. They can't be at 90 degrees out of phase. The phase difference is 180. Then the amplitude, because they are separated by half wavelength, there is a possibility that actually the amplitude is always going to be the same for two particles separated by half wavelength. The amplitude is going to be the same. Therefore, the answer is going to be D. A parallel beam of red light of wavelength 700 nanometers is incident normal on a diffraction grating that has 400 lines per millimeter. What is the total number of intensity maxima? That is now very easy. N lambda is equal to D sine theta. For N maximum, sine theta is equal to 1. They have given us D as lines per millimeter. Remember, D is 1 over N, where N is the number of lines per meter. So number of lines per meter is going to be 400 times 1000 to change it from per millimeter to per meter. So N is going to be D, which is 1 over N, that is 400,000. Sine theta is equal to 1, so divide by wavelength, that is times 700 times 10 power negative 9. So this is going to be 1 divided by, open brackets, 400,000 times 700 exponent negative 9, which gives us 3.57. We round off this to 3. We shall not round off to 4. We round off this to 3. But remember, I have demonstrated this, that if this is the grating, there's a central order maximum, then there will be n equals to 3 up and n equals to 4 up, 3 down. So we have 3 plus 1 plus 3, or 3 times 2 plus 1, which gives us a total of 7. So there are 7 intensity maximum. Total there will be 7. Two wave sources are oscillating in phase. Each source produces a wave of wavelength lambda. The two waves from the sources meet at point X with a phase difference of 90 degrees. What is a possible difference in the distance from the two wave sources to point X? That is the path difference. So we know path difference. Because they have given us the phase difference, so we shall simply say phase difference. We shall start with the phase. It is easier to start with the phase difference. So the phase difference phi is equal to 360 degrees into the path difference, which is the distance between the two, divided by the wavelength. So they have said, what is the possible difference in the distance from the two wave sources to point X? So 90 is equal to 360 into X over lambda. So this is going to be 90 over 360 times lambda, which is 1 over 4 times lambda equals to X. So the answer here is going to be lambda over 4. Which statement about electromagnetic waves in a vacuum is correct? Amplitude is inversely proportional to velocity. Amplitude is inversely proportional to velocity. That does not make sense. Frequency is inversely proportional to wavelength. I think that is very true. For constant speed, since electromagnetic waves have this constant speed, and v is equal to lambda f, it means f is inversely proportional to wavelength. A transverse wave travels along a rope. The graph shows the variation of the displacement of the particles in the rope with the distance along it at a particular instant. At which distance along the rope do the particles have maximum upwards velocity? Maximum upwards velocity. Since it is displacement against distance, it is a graph of displacement against distance. When the displacement is zero, many times the velocity is maximum. When the displacement is zero, the velocity is maximum. Particles here on this side are vibrating vertically upwards until they reach this point where they are at rest. Particles here are vibrating downwards on this side up to that point. Particles here are vibrating upwards, and so on and so forth. So we want a maximum upwards velocity. So the answer is going to be around here, which is approximately half of 1.0, which is 0.5. So our answer is going to be A. Here at 1.5, it is vibrating maximum velocity, but downwards. 2.5 maximum velocity upwards, but 2.5 is not indicated here. So our answer is going to be A. Here, particles on this side vibrate upwards. That's why we have a crest here. A trace is shown on the screen of a CRO here. So this is our trace. Let's check for one complete cycle. We have two cycles are taking 1, 2, 3, 4 boxes. So two cycles are taking 4 centimeters. That means one cycle should be taking 2 centimeters. If two cycles are taking 4 centimeters, then one cycle should be taking 2 centimeters. The time-based setting is 2.5 milliseconds per centimeter. The Y gain is 2.0 volts per centimeter. What is the frequency and amplitude? Let's start with the amplitude. The amplitude, we have two boxes, 2 centimeters. So the amplitude is going to be 2.0 times 2, which is 4 volts. So we eliminate this one and this one here. Then we check the frequency. So the frequency is going to be equal to 1 over period, which is 1 over the length representing one cycle times the time-based setting. The length representing one cycle is 4 centimeters. The time-based setting is 2.5 times 10 power negative 3. So we have 1 divided by 4 times 2.5 exponent negative 3, which gives us it was 2 centimeters. One cycle is 2 centimeters, so this is 2. So that is 200. Did I do it wrong? 1, 2, 3. 1, 2, 3. Sorry. These are 3 centimeters, which is 1.5. Yeah, those errors are expected. So this is 1.5. My eyes may not be very good. So this is 1.5 times 2.5 exponent negative 3. 1 divided by the answer. That is 266. So F is 266.6 recurring, or approximately 267. So our answer is going to be C. A high-speed train approaches a stationary observer at a speed of 80 meters per second. The train's horn emits a sound of frequency 250 Hz. The speed of sound is 340. What is the observed frequency of the sound from the horn? So we know that frequency is equal to observed frequency is going to be V over V because it is approaching, so it is going to be minus Vs times the frequency of the source. So that is 340 divided by 340 minus 80 times 250. So 340 times 250 divided by 340 minus 80. So we get this as 326. And if it is 326, that is approximately 330. So our answer is D. Which row shows the correct frequency in hertz for each of the four principal radiations? So it is hard to tell the frequencies, but it's easier to deal with the wavelengths. Let's just check. We can just sample a few of these ones. Of course, wavelength is equal to V, or speed, which is 3 times 10 power 8, divided by frequency. Let me start with the microwaves. Starting with microwaves, 10 power 10. What is the wavelength? 3 exponent 8 divided by 1 exponent 18. So that gives me 3 times 10 power and negative 10. That can't be the frequency of, that can't be the wavelength of microwaves. That means A is wrong. That means A is automatically wrong. Let me check 10 power 10. I'll just say 3 exponent 8 divided by 1 exponent 10. This is 0.03, which is 3 times 10 power negative 2. That is the frequency wavelength of microwaves. So the answer is going to be D. I just randomly chose to check microwaves wavelength. You could also check the wavelength of X-rays or ultraviolet and find out which is the most appropriate. But when I check the frequencies to get the wavelength of microwaves, I get the last one, 10 power 10, gives me 3 times 10 power negative 2 meters, which is microwaves. A pipe of length 100 centimeters is open at both ends. A loudspeaker situated at one end of the pipe can emit sound of different wavelengths. At which wavelength can a stationary wave be produced in the pipe? So the length is 100. So at which wavelength can a stationary wave? It is open at both sides. Let's first look for the fundamental. For the fundamental, 100 would be equal to half wavelength. So that means wavelength would be equal to 200 centimeters. Then the frequency, fundamental frequency, our frequency is going to be equal to, so if the wavelength is equal to twice, is 200 centimeters, fundamental frequency will be V divided by lambda, which will be V divided by twice L. So that is the fundamental frequency, V divided by 2L, or V over 200. So for an open pipe, Fn is equal to N times F naught, where N is a whole number, where N can be 1, 2, 3, 4, and so on and so forth. Also, if we want to look at it in terms of length, the wavelength is always going to be the wavelength. Of course, the wavelength, the next one is going to give us the next one. If we were to increase this, the next one will be n equals to 2, n equals to 3, and so on and so forth. Now, when you look at 75, let me just divide 100 by 75. That gives us a decimal, which is not a whole number. 100 by 75, that's not a whole number. 150 or 100 by 150. 100 divided by 150, that's not a whole number. 100 divided by 300, it's not a whole number. Then 100 divided by 50, it gives us a whole number. So automatically this is going to be 50 without even wasting any time. So the length should be divisible by the wavelength exactly for an open pipe. For an odd pipe, the wavelength divisible by divided by the length divided by the wavelength would always give us half wavelength, or it will always give us 0.5. Always give us that 0.5. Monochromatic light is incident on diffraction grating, and a diffraction pattern is observed, which row shows possible effects of replacing the grating with one that has twice as many lines per millimeter. So for diffraction grating, n lambda is equal to d sine theta. Which row shows possible effects of replacing the grating with one that has many lines per millimeter? Remember, d is 1 over n. When n increases, d decreases, so d has decreased. Number of orders of diffraction visible. Of course, n decreases when d decreases. So number of orders decreases, that is true. So this one is wrong. Those ones are wrong. Then angle between the first and second orders of diffraction, we see that the angle is inversely proportional to d. When d decreases, the angle must increase. D is inversely proportional to sine theta. When d decreases, sine theta must increase. Therefore, the answer is going to be B. Monochromatic light of wavelength lambda is incident on two narrow slits, S1 and S2, a small distance apart. A series of bright and darker fringes are observed on a screen a long distance away from the slits. The nth darker fringe from the central bright fringe is observed at point P. The nth dark fringe is observed from the central bright fringe at point P on the screen. Which equation is correct for all possible values of n? So remember, for a darker fringe to be formed, the path difference lambda is going to be n plus a half wavelength. N plus a half wavelength. The nth darker fringe from the central bright fringe is observed at point P on the screen. Which equation is correct for all positive values of n? Positive values of n. So we can check n equals to 0, 1, 2, 3, and so on and so forth. So we can check for all possible values of n. Of course, this one is not going to be correct. N is equal to 0. If n equals to, okay, let's start with n equals to 1. If n equals to 1, this is lambda over 2. That will be the first order. N equals to 2. n equals to 2, this will be the path difference will be lambda, and that will be constructive interference. That is wrong. N equals to 1, this is constructive interference. N equals to 1, this will be 1 minus a half, which means it is positive a half lambda. If it is 2, it will be 2 minus a half, which is going to be 3 over 2 lambda. If it is 3, it is going to be 5 over 2 lambda. If it is 4, it will be 7 over 2 lambda. So this is correct. We can check this one. N plus a half lambda. It means for the first possible positive value of n, it means this is going to be 1 plus a half times lambda, which will be 3 over 2 lambda. It means for n equals to 1, it is starting with the third order. That means the most appropriate is going to be C, because C starts with the first one, which is 1 over 2 lambda, the first order. Okay. However, if normally when we use this equation here, n is equal to 0, 1, 2, and so on and so forth. But this one here, it means we start with n equals to 1 and so on and so forth. So if it was starting from n equals to 0, here they said all possible values of n. That means 0 and negative values are not inclusive. That's why this is not working. Okay, what is a typical value of the wavelength of microwave traveling in a vacuum? I think we now know that microwave is at 10 power negative 2 meters, or 10 power negative 3 maximum. We can check these wavelengths. We have 300, this is 3 million pico, that is 3 million exponent negative, pico is negative 12. 3 million exponent negative 12, that is 3 times 10 power negative 6, so that is wrong. Nano, that is 30 exponent negative 9, that is also wrong. 30,000 micrometers, 30,000 exponent negative 6. It is giving us 0.303, which is 3 times 10 power negative 2. So the answer is going to be C. The displacement time graph for a layer of air in the path of a sound wave is shown here. Which wave quantity is increasing? Which wave quantity is increasing? The displacement time graph for a okay, let's look at this. This is one cycle taking this period. The next cycle you see it is taking a shorter period. So the period here is shorter, and we know period is inversely proportional to frequency. So the period has decreased, the frequency is increasing. Therefore, the answer here is going to be frequency. Diffraction can be observed when a wave passes an obstruction. The diffraction effect is greatest when the wavelength and the obstruction are similar in size. For waves traveling through air, what is the combination of wave and obstruction that could best demonstrate diffraction? Waves traveling through air. Microwaves passing a steel post. Radio waves passing a copper wire. Sound waves passing a human ear. Visible light waves passing a gate post. So this one is the wavelength of visible is very small compared to a gate post. The sound waves have a longer wavelength than the human ear. You can find the estimate wavelength of sound waves, which is speed is 330. Depending on the frequency which is detected by the human ear, which is around 20,000. Let's check the wavelength. 330 divided by 20,000. So this is also very small. The wavelength is 0.016. Let me multiply this by 100. That's 1.65 in meters. in centimeters, 1.65 centimeters. Radio waves have a wavelength of around 1 times 10 power 3 meters. Around passing a copper wire, they have a very longer wavelength. They may not undergo a good diffraction. Microwaves passing a steel post. So the best combination for waves traveling through air. What is the combination of wave and obstruction that could best demonstrate diffraction? So microwaves passing a steel post. So the best answer would be A. Microwaves passing a steel post. Note that the wavelength of microwaves is approximately 10 power negative 2 in meters, and the diameter of a steel post could be approximately that value. Light of a particular wavelength is emitted from the sun at any instant. A band of wavelengths ranging from less than lambda s to more than lambda s is observed in the Earth. This is caused by the Doppler effect. What could be the explanation for this Doppler effect? The sun is moving at right angles to a line joining the sun and the Earth. The sun is moving away from the Earth. The sun is moving towards the Earth, and the sun is rotating. I think it's because the sun is rotating. Light of a particular wavelength, lambda s, is emitted from the sun at any instant. A band of wavelengths ranging from less and then more. That means the sun must be rotating. If there is a band ranging from less and then more, then the sun must be rotating, because its speed even keeps changing as it is rotating around. It is rotating about itself. That is, it is spinning. That is what be meaning. The sun must be rotating. If the observer observes frequencies ranging from less than lambda s to more than lambda s, that means the sun must be rotating. Okay. What is the order of magnitude of the frequencies of electromagnetic waves in the visible spectrum? We can just check the wavelength. We know the wavelength in the visible spectrum is 10 power negative 7 in meters. So frequency must be speed, which is 3 times 10 power 8 divided by 10 power negative 7. So this gives us 10 power negative 15. So the answer is going to be 10 power negative power 14. Because 3 times 10 power 8 divided by 10 power negative 7 gives us 10 power negative 15. So that means the closest is going to be most likely 10 power 14 hertz. You could also check the other way around. Check the wavelength, which is speed, 3 times 10 power 8 divided by the frequency, which is 10 power 14. For a visible spectrum, the answer should be of the range 10 power, close to 10 power negative 7 for wavelength. 3 exponent 8 divided by 1 exponent 14, which gives us 3. No, it is, yes, 3 exponent 8 divided by 1 exponent 14. That is 3 times 10 power negative 6. What is the order of magnitude of the frequencies of electromagnetic waves in the visible spectrum? I have to check this again. Let me check 10 power 16. 10 power 16, lambda is going to be 3 times 10 power 8 divided by 10 power 16. 3 exponent 8 divided by 1 exponent 16. That is 3 times 10 power negative 8. So 3 times 10 power negative 8 is already beyond. That is already less than 4 times 10 power negative 7, which is the smallest. Let's check on the left hand side. Let's check 10 power 12. 4 exponent, 3 exponent 8 divided by 1 exponent 12. So this is even smaller. That means the most appropriate will be 10 power 14 hertz. Okay, let's stop part 4 at this point. We shall start from this question in part 5. I hope you will learn something from this video. In case there are errors, you can always let me know. I'm human, I'm bound to make those errors. Nevertheless, thank you for watching this video. See you in part 5. Bye bye.